All right, so we are looking at 7.4 here in Trig, and I apologize, I'm a little under the weather, so it just is what it is. So we will get through this fairly quickly. What we're going to talk about in this section is reference angles, and reference angles are going to become very, very, very important when we're solving trig functions and what we're going to be doing in the coming days. So this first slide is super important for us to understand how this works, and what a reference angle is every time that we try and find the sine or the cosine, or even sometimes the tangent of something, we need to know what the degree or what the radians are going to be. So we're going to look at this slide, so you can take notes as needed on this slide, but I'm going to use a new sheet of paper that allows us to see this in kind of a bigger, so it's a little bit bigger, so it's easier for you to visualize it. So hang on here a second. Okay, so what we're looking at here is we're looking at a normal circle that we've, kind of gotten accustomed to using here. And let's not worry about this little thing right here. Don't worry about that circle. But the idea is that every time we get an angle, so if I get, say, a 30-degree angle, what we do is we're drawing, that means that we're at a line where this angle is 30 degrees. Well, when we figure out what the sine and cosine are, we're always going to use that 30-degree angle. The problem is that if I give you, say, an angle that is, we know this is 90 degrees right here, but let's say we give an angle that's 120 degrees. Well, 120 degrees, would give us a line that looks about right here. But here's the deal. Our 120 degrees is all the way from the beginning. That's 120 degrees. But we can't use that when we do our triangle. And that's what's really important, is we always are creating a right triangle that comes straight down to the x-axis no matter where we're at. So if I draw in another angle right here, then our triangle always has to come to the x-axis. So the problem is we always need to know what the angle is in between the line and the x-axis that we're dealing with. So right here, even though it's the, say, sine of 120 degrees, when we actually try and solve it, we have to use what a reference angle is. And a reference angle is basically the amount of degrees that are, sorry about that, the reference angle is going to be the number of degrees that are left to the x-axis that we're at, or the number of degrees that we've gone from the x-axis. So this one right here, again, we've gone 120 degrees. This is 180 degrees right here. So 180 minus 120 is 60 degrees. That's our reference angle. So that means 120 degrees reference angle will always be 60 degrees. And then again, if we go down here and we say that this is, say, 210 degrees. So we'll say that this line right here went all the way around to be here. And let's say that was a 210 degrees. Again, we're not going to use 210 degrees when we do a right triangle. We've got to do what is left from this x-axis. So we're really only looking for the angle from here to there. Again, 180 degrees, we know that's 180. That makes up 180 of the 210. So what's left over? 30 degrees. So our reference angle there would be 30 degrees. And that's basically the gist of what a reference angle is going to be, is we're always going to go from x-axis to the line. Again, if the line was over here, then we would be looking for what is this angle right here, and we can figure that out because we would probably know what the degrees are all the way around, and then we could subtract that from 360. Okay, so always think about how many degrees you've gone total, and then maybe how many you have left, or how many past 180 you went, or how many past 90 you went, and that will help you, okay? So hopefully that makes sense. We'll work on that more in class, but this is the most important thing for you to understand out of this section, is how to understand where to find a reference angle, and and how to find it. So it's really a simple concept, but you just got to get used to it. All right, so let's go back to the slides that we're working on. So let's talk about special right triangles. This is going to be the foundation for all the trig that you use. Special right triangles are 30, 60, 90 triangles and 45, 45, 90 triangles. What you need to remember, and this is the only thing that I think you should need to memorize, is what these sides look like. A 30, 60, 90 triangle will always have the ratio of these sides. Square root of 3 is always opposite of the 60 degrees. 1 is always opposite of the 30 degrees, and 2 is always the hypotenuse. On the 45, 45, 90, your two legs are always the square root of 2, and your hypotenuse, again, is 2. And it can be any ratio of these. So like I can multiply every side by 3. So if I multiplied every side by 3, then this would be 6, this would be 3, and this would be 3 times the square root of 3. And it's the same thing. It's still a 30, 60, 90 triangle because it shares that ratio. But this is really important because now that we have this, I can now say, what is the sine of 30 degrees? And you'd say, oh, well, I know that sine is opposite over hypotenuse, so therefore the sine of 30 degrees is 1/2. Or I could say, what's the cosine of 45 degrees? And you say, well, I know that cosine is adjacent over hypotenuse, so it'd be the square root of 2 over 2. And then you could keep doing that. So the idea is we should always be able to find sine, cosine, and then eventually tangent in any of these 3 degrees that you see. Sine of 30, cosine of 30. Sine of 60, cosine of 60. Sine of 45, cosine of 45. And we should be able to do all of those. Okay? So now filling in this chart right here, excuse me, we can use these triangles. So we've already talked about the sine of 0. Because sine is our y value on our circle, we know that sine of 0 is 0. Cosine is our x value, so we know that cosine of 0 is 1. Now we go across. Pi over 6 and 30 degrees are the same thing. Let's look at this. Sine of 30, we've already defined it as being 1 over 2. Cosine of 30, adjacent over hypotenuse, square root of 3 over 2. That's square root of 3. Try and fix that. Okay? Sine of 45, square root of 2 over 2. Opposite over hypotenuse. Cosine, adjacent over hypotenuse. Square root of 2 over 2. Go to 60 degrees. Sine, opposite, square root of 3 over hypotenuse. Square root of 3 over 2. And then the cosine, adjacent 1 over 2. And then we have the sine of 90. Again, that is that vertical line like what you see down here. Our sine is our x value, so that's going to be, our sine is our y value, so that's going to be a positive 1. Cosine of 90, that's our x value, that's going to be 0. Now, one thing you should notice is these are completely reverse of each other. This goes 0, 1/2, square root of 2 over 2, square root of 3 over 2, 1. This one goes down from 1. 1, square root of 3 of 2, square root of 2 over 2, 1 over 2, 0. And it keeps cycling. That's what a sine and cosine function is. It's just a perfect cycle, and it just keeps going over and over again, the exact same numbers. This one would start going back down towards 0, and then it would go negative. This one will continue to go negative until you get to -1, and then it'll start going back up to 0 again, and then go positive. It's a complete cycle. So let's see what it looks like when we graph it. Okay, and I know this graph's pretty small here, but you can see it on your paper probably a little bit better. So we know that the cosine, or we'll start with the sine graph. So the sine graph starts right here at 0, and then we said that the sine of 30 is 1/2. Then we said the sine of 60, we'll skip over that. Sine of 90 is 1. And then, like I said, we can keep going from there. We know that the sine of 180 is going to be 0. And you can pretty much assume that the graph is going to look like this oscillating curve. And it'll be perfect. It will continue to have the same values over and over again. Now, our cosine graph always starts at 1, a regular cosine graph, and it comes down to 90. Cosine of 90 is equal to 0. And again, you can get the same idea of what a cosine graph looks like. It looks almost exactly the same. You know, if we were to continue it over here, it looks exactly the same as a sine graph. It's just shifted a little bit left and right. But that is what the basic graphs of sine and cosine look like, okay? We're not going to worry about this slide right here. This is just a review of what we did before. But again, this is very important for you to understand this diagram and how to determine what our angles will be. So this is something we did on our homework that was really tough. You know, cosine, and I guess we'll just review it real quick. Remember, cosine is your x value, and sine is your y value. So if you know that your y value has to be equal to 0, your y value is equal to 0 at this point right here and at this point right here. So you just need to determine what your thetas are at those 2 points. And this theta right here is theta equals 0. It also equals 360, and then everything after that. And then over on this one, theta is equal to 180, and then 540, and all of those multiples each time that it goes around the circle. Now, if we were doing it in radians, we have to remember that that's 0 and 2 pi is this one, and the other one is pi, and then and then 5 pi over 2. And again, all you're doing is adding 2 pi each time. But we need to understand where these values are equal to 0 and 1 and -1, etc. So, okay, that's it for this video. Don't forget to take your quiz, and I will see you in class.